Yeah, hello. Good morning, everyone. So, if you're able to hear my voice and see my screen, then please type Y in the comments. Okay, then we'll start. So, we were discussing about how to get the Mel frequency Cepstral coefficients and the step-by-step process of it. So, the first step we discussed is pre-emphasis. We discussed a lot about pre-emphasis. In fact, we discussed quite a lot about pre-emphasis and why is it required, why is it beneficial, particularly from LP analysis point of view. We also talked that uh, speech has a spectral slope of minus 6 dB per octave. So if we do pre-emphasized speech, if we do our analysis on pre-emphasized speech, then we will get rid of that spectral slope to a large extent, and we'll be able to observe whatever is there, the information in the high frequency spectrum in a better way. So then we said we'll do our typical framing and windowing that we have talked about so much early in our earlier lectures. But you can do this pre-emphasis and frame blocking and windowing means in alternatively as well. Means step one and step two, you can replace them as well. You can first frame and frame it, then do pre-emphasis and then window. Please don't frame it, window it, and then do pre-emphasis. Do the opposite. Means either you do the entire speech signal is their entire whatever 3 second, 4 second, 1 minute does not matter. First you do pre-emphasis and then you do frame by frame blocking and what is called frame by frame segmentation and windowing on each frame. Or you can also do first framing, then you from within that you do this pre-emphasis, and then you can do your windowing. But it won't matter much. I think even if you do framing and then windowing and then do pre-emphasis, it won't matter much actually in the performance. But anyhow, let's stick with the most standard way. The best way is this is a single operation. If you do pre-emphasis once, that's done for the entire speech signal, entire speech utterance, and then you can do framing and blocking, so framing and windowing. So let's stick with that. So then once we have our windows, we do our discrete time Fourier transform, and then we use the Mel spectrum, the Mel filter bank. We superimpose the Mel filter bank on top of our power spectrum. What is the power spectrum? So after windowing we have at any point, okay, let's see, this is our signal windowed at a particular point n, and I am taking the index as m. Okay, this time domain index. So whatever the signal comes in that, this is your center, and whatever the signal looks like, the speech signal in that. Okay, now from that we have Sn e to the power j omega. But instead of just taking magnitude, we will take magnitude square. If I take magnitude, if I take magnitude, so this is omega minus pi to pi. This is the range of digital signals. So, uh, this is your magnitude spectrum. If you take the square of that, this is called the power spectrum. Or actually, it is not appropriate to call it the power spectrum, though we loosely use it. It could be said as the estimate of the power spectrum, also called as this estimate of the power spectrum, that magnitude squared. This is also called as periodogram. But in loose terms, we say power spectrum and periodogram, or square of the magnitude spectrum is power spectrum. We loosely use these terms, but in pure technical terms, in absolute correct technical terms, it is an estimate of the power spectrum of the signal. And why is that? You will, if you go through your statistics, you will understand. And the more accurate name is periodogram. So once you have this, sorry, yeah. So once you have this, you will impose this filter bank on top of that. So the Mel filter bank that we got. Mel filter bank, I will convert into our analog scale. Okay, I'll represent it all this in analog scale. I know digital frequency is minus pi to pi, but we have talked about earlier in our revisiting our digital signal processing basics, how we represent omega equal to omega ts. This is analog. So it is easy to visualize and understand things in terms of analog frequency. So even though we are dealing with digital signals, when we represent them, when we visualize them, we take the axis in terms of analog frequency. We have talked about all this anyhow. So here we have our S n e to the power j omega whole square, whatever spectrum that comes out. This is not log, this is a simple magnitude spectrum. This is not log spectrum or anything. Whatever comes, I don't know, whatever comes. Whatever is up to your maximum frequency of the signal. If your Fs was your sampling rate, Fs by 2 will be your maximum frequency. Nyquist, this, hope you know all this. Anyhow, so we have this Mel filter bank. Where this is a straight line equation, this is a straight line equation, this is a straight line equation, this is a straight line equation. We'll go talk about that straight line equation. But you have a triangular filter at any point, a set of triangular filters motivated by the critical band theory. How is it? What is it motivated by? The critical band theory and masking. Those two things we talked about at length. Today we will also see some. I'll share some videos that we'll watch, that will clarify this critical band theory and masking. So anyhow, we have a good idea of critical band theory and masking by now, but still, we'll watch some good videos regarding that matter. Anyhow, proceeding forward. So we have this. So if we, let's say, let's take a different eye. Let's say any of this filter we are this one I am putting it there, where this height is 1. Remember, this is 1. So then we multiply and we take the area under the curve. Basically, that means we take the mean. So whatever it is, if I say this is f, if this is your emmet filter, this is your emmet filter, so this is fm, So this is f minus m, center frequency of the previous filter is f minus 1, fm plus 1. So we'll do from f minus 1, or even if you don't do, does not matter, because outside it the filter is 0. The filter outside this range is 0. So if you, even if you take whatever range it is, 0 to fs by 2, the whole spectrum you take does not matter. So Sn e to the power j omega whole square. Here we can say this is some, we give it a notation, some, since the filter generally represented by h, so let's say h e to the power j omega. And what we'll do, so it gives weighted with respect to this, the power spectrum of the signal weighted with respect to the triangular filter, weighted by the triangular filter. We get the mean of that. This is the mean. This is the mean of the power spectrum weighted by this triangular filter in that particular frequency range, which is given by the uh, range or the frequency range of the triangular filter. So in a set of, so we have said that we use around 24, then 24 is the number. So in 24 filters we have, we generally choose 24. So if we have 24 such filters in a MEL filter bank, so after doing that operation, we'll get 24 energy values, the power spectrum that we get, or power values, whatever you say. So since you are integrating power, we say it's energy. Okay, so 24 energy values corresponding to each of these filters. So now we'll go for Cepstral analysis. So what we do is this 24 energy values, whatever you, let's see, maybe here it's there. Yeah. So yes. So let's, yesterday we were talking about how the triangular filter, how can be expressed in mathematical form. It's an easy thing, but if you still want, I will revisit it. So let's put it here. It's side by side, maybe. So any emmet, this is the emmet triangular filter. So fm minus 1 was the center frequency of the previous, fm plus 1. And this is 1. So you have at fm 1, fm minus 1 equal to 0. So y equal to mx plus c. So there are two unknowns, two values given. So y and c you can find. So outside this m minus 1, these are, as I said, represented in DFT frequency bins, but which is the way to implement. But in mathematical form, it is better to represent in the DFT, or discrete time Fourier transform, instead of discrete Fourier transform. So I am talking in terms of discrete time Fourier transform. So anyhow, so if you see, so below f minus 1, if omega or f is below f of m minus 1, then triangle does not exist, 0. Again, greater than m plus 1. And within this range, then you find out what will be your straight line from this equation. Again, in this range, you find out the equation of the straight line, because you know at fm plus 1 it is 0, at fm is 0. Two equations are there again. So that's how it's quite easy. I hope you understand this part. So now you did all that. Yes. So now comes, so you have 24 energies. You had 24 energies. So 24 energy values you got because there were 24 filters. Take the log of these energies. Here it is said as M. You can take something else. You can say E of M if you want energy. Okay, let's take, let's say E of M. So energies you got. What is of the MEL filters in the MEL filter bank? So once you get this energy, then you do discrete cosine transform. And how is discrete cosine transform? If this was some xn, so there are many types of discrete cosine transform. This is the most standard form. It is called DCT2, if I'm correct. So anyhow, we take discrete cosine transform. But why is it Cepstral? If you remember Cepstral analysis, what did we do in Cepstral analysis? In Cepstral analysis, if we got any x e to the power j omega, or let's say s n e to the power j omega. Okay, so what did we do? We took the log of the magnitude spectrum, or in that case we generally used ln, but nobody stops you, means ln is basically just difference in the base. So we took the log. Nevertheless, we took the log of the magnitude spectrum, and then when we did Fourier transform of that, we got Cepstral coefficients. Okay, and if we did only simply that simple spectrum, if we took log, we got the complex Cepstral. We got these values, what we call as Q friend C, and then we did high time lifting, Newton lifting, and all that. So same way, now we are taking log base 10 of the energy values, and instead of Fourier transform, we are taking discrete cosine transform. The advantage is our objective is here, so whatever 24 values are there. So m equal to 0 to m minus 1, so 0 to 23, so 24. So you took, so you will take DCT. So the advantage is that if you take Fourier transform of this, it again Fourier transform of this, then it will again, because this is an exponential term there, it will come out as exponential. But our objective is not that. We have these energies. DCT is called a compression algorithm. Means all these energies that we are getting, we are representing in a complex set of coefficient. A compressed, more compact form. That is the idea. So we take DCT, and then whatever coefficients we get, which is called the MEL frequency Cepstral coefficients. Okay, these we will get 24 coefficients, but we will see that about 10 to after 10 to 13 coefficients, these are really almost zero. So generally neglect them. So the first around 10 to, you can say maximum 15, 10 to 15 coefficients we keep, and the rest we discard. Those, so it now becomes a 10 to 15 dimensional vector for every frame of speech. We can do it, and we can do this, extract this MEL frequency Cepstral coefficients, and we'll get a 10 to 15 dimensional vector. This set of numbers that we express it in vector form, okay, this set of numbers are extremely important. They are have been found to be extremely important for all speech processing applications. So now going back to DCT, so how do you take DCT? This is the formula. If you have a set of whatever numbers are there, xn equal to 0 means m minus 1, this is just a range. So in our case 0 to 23. So whatever you do, cosine pi and this is as if, you know, in Fourier transform e to the power j omega n is used. This is cos of omega n plus j sine of omega n. So we are taking only the cos term. There are benefits of taking discrete cosine transform, because it has been found you could also have taken discrete sine transform, that also exists, but we found that discrete cosine transform gives better results compared to discrete sine transform and other similar algorithms, other similar transforms, and so on and so forth. So it behaves in a more compact manner, and it has been successful in many applications. And we also avoid generating unnecessarily complex numbers, because our aim is not to do Fourier analysis of these energies. Our aim is only to represent them in compact form. So traditionally here only 8 to generally 10 to 15 is used. And the 0th coefficient is often excluded. Why? See, if you put 0 here, C of 0, okay, so M becomes 0, and so no, so N becomes here 0, so cos 0 is 1. And what is this? So you are taking the log of whatever log of this values where the log energies were there. You are just summing up all the log energies. So indirectly you are taking the sum of the, finding out the energy of the signal, and that has not been found to be very useful. So generally zero coefficient C0 is excluded. What happens is, yeah, if you see it comes out as log of 10 of E of M. I'm representing here, it is representing as S of M. Then M equal to 0 to 23 basically. So it is sum of all the energies of all the Filterbank energies. So indirectly it is like the sum of the signal, weighted sum of the signal. So the weighted sum of the signal, because from Parseval's relation, if you know the integration of the power spectrum will give you the total energy in is same as taking the energy in the time domain. So anyhow, so let's talk about this dynamic MFCC features now. So what I will do, yeah, let's talk about like this. So for every frame, so you have the speech signal, whatever it is. So you do frame by frame analysis, windowing, you did pre-emphasis and all that. But anyhow, frame by frame analysis you will do. So let's put frame number 1 to whatever number of frames are there, some from frame n. For each frame you got MFCC. Let's say you took only 13. 13 is a standard number that is used in MFCCs. First 13 coefficients after you get DCT. So every frame you get 13 coefficients. So you can represent it as a row vector. Now in speech, it is a dynamic signal. So what happens is, we also want to see how this, because these certain coefficients are giving information about that speech signal in that particular frame. How the speech signal is varying from one frame to another. How are these characteristics varying? That also becomes very important, particularly in applications such as speech recognition. Actually, not even speech recognition, all forms of, all applications of speech, because speech is the way, for example, let's say speaker recognition, the way you are able to when you utter a continuous word, the way it varies for you, because everyone's vocal tract is different. The way your sounds vary to give a complete word, it is slightly different from your friend. Similarly, for different emotions, for example, if you're speaking the same word but in a different state of mind, those variations will be reflected. So what we do is, apart from this MFCCs, we go for what is called velocity and acceleration coefficients. So what is velocity coefficient? So you have this C0 to C12. So we'll take that forward or backward difference or both. So how it is changing. So what we do is this. Let's say t equal to 3. Okay, so means you have some value ki. We don't know that at the moment. C of some n minus 1 for a particular coefficient. Okay, plus, so k of minus 1 basically, plus k of 0 c of n plus k of 1 c of m n plus 1. So we are taking around for that particular coefficient, whatever coefficient we got in the previous frame, whatever coefficient we got in the next frame, and then we do a kind of averaging or difference, how you put it. For example, if I take k1 equal to 1, okay, k0 equal to 0, and k minus 1 equal to minus 1. So what I am saying, I am neglecting the current coefficient. I am taking how my next frame, this coefficient, this particular MFCC coefficient, whatever it is number, mth MFCC coefficient, how it is varying from my previous frame to the next frame. Now you could choose other numbers for ki also. For example, for kn, for example, okay, if for k0, you could choose 1, k of 1 equal to say 0.5, k of minus 1 equal to say minus 0.5. So you want to somehow, you want to find out that how it is changing, that coefficient is changing over different frames. So obviously, why is it called velocity? Because velocity is the rate of change. So if you have a distance, how your distance is changing over time, that is velocity. So in the same manner, we have this velocity coefficient. Once you get your MFCC coefficients, we can get your delta MFCC. All the MFCC coefficients for all the frames, if you get, only then you can get for each and every frame, you conduct this velocity, you extract these velocity coefficients. These are also called delta MFCCs. So for every frame, 1, 2, 3, 4, you get your velocity coefficient. Now, once you get your velocity coefficient, how is your velocity coefficients? We call acceleration. What is the rate of change? This is how, what is the change over time? What is the rate of change or acceleration? That is called delta MFCCs. Delta MFCCs. So again, the same process. Once you get your delta MFCCs or velocity coefficients, you then apply that same philosophy, the same process that that we talk about here, and you will get your delta coefficients. So in together, so what you will get, your 13 MFCCs, you will get 30 delta coefficients, you will get 13 acceleration coefficients for each and every frame. And that gives you a 39 dimensional MFCC vector for each frame of the signal. If you had chosen, let's say 15 or 20, I don't know. If you had chosen 20 Cepstral MFCCs first, then you would have got ultimately 60 dimensional MFCC, 60 dimensional MFCC factor. So that's it. So what I want now is I want to clarify, I want you to gain more clarity regarding these auditory filters, and auditory filters means our central band theory and masking. So there are two wonderful videos that I want you to watch. Please come back at 9:45 and we'll conclude the lecture, but please watch in your leisure after this class or whenever you get time. This will clarify your doubts, or it will make everything more clear. What is auditory masking and what is the central band theory or auditory filters, what are they? There is also a short Wikipedia, and there is also a good Wikipedia page on discrete cosine transform if you want to go in detail. But it's really easy. It states the advantages of DCT over other transforms, and where is it used mainly for completion. So this is a Wikipedia article. So come back at 9:45 and we'll close the lecture. Then please watch this videos. So hello, please come back. So as you see, those videos are around 30 minutes and one is around 15 minutes, something like that. So take your time and please give your attendances, and we'll close the lecture now. And please exit the lecture after you please give your attendances in the Excel sheet. Okay, thank you.